Hello and welcome to this video for CE 105-205. So in the previous video, we reviewed what are the four Zachariasen rules. The four Zachariasen rules will tell you if you have a given binary oxides where you have a cation A and some oxygen atoms O, and you have a given stoichiometry where each cation, you have M cation that are combined with N oxygen atoms. The Zachariasen rule will tell you four conditions where if each of those four conditions are satisfied, then this oxygen, oxide is likely to form a glass. But if at least even one of those four rules is not satisfied, then this oxide is not likely to form a glass. It's likely to form a crystal upon cooling, upon quenching. So as a reminder from the previous video, the four rules are that first, the coordination number of the cation needs to be either the coordination number of the oxygen needs to be either 1 or 2. So that's the first rule of the four rule of Zachariasen. So the coordination number of the oxygen is either 1 or 2. Cannot be 3, cannot be lower than 1 on average. Second rule, it's now the coordination number of the cation. The coordination number of the cation needs to be 3 or 4. Cannot be larger than 4, cannot be lower than 3. So that's the second rule. Third rule, now it's about the types of connection between the polyhedra around the cation. It needs to be only corner sharing units. So if you look at two neighboring polyhedra, they should only share one corner. They cannot share two corners, they cannot share an edge, they cannot share three corners, so that they cannot share a face. So it should be only corner sharing connections in between polyhedra. And then the fourth rule is about the number of corners that are shared between the polyhedra around the cation. Around each cation, there needs to be at least 3 corners of each cation that are shared with other cations. So you cannot have too many corners of the polyhedra that are terminating. At least 3 of them needs to be shared. So there needs to be at least 3 shared corner around each polyhedra. So that those are the 4 conditions of Zachariasen rules, and what we will see in this video is how we can apply and check if those 4 rules are satisfied for different types of binary oxides. So the first example that we are going to see is the case of silica SiO2, where in that case the cation A would be silicon, and each silicon is combined with 2 oxygens, so M equal 1, N equal 2. So in that case, we know that silica is a very good glass former. It's very easy to form a silica glass. It's one of the substances that is the easiest to form a glass, to vitrify upon quenching. So clearly we should find here that silica satisfy the 4 Zachariasen rules. So let's check that. So the first thing is to look at the coordination number. So for this, what we know is that the coordination number of silicon is 4. So each silicon is connected to 4 oxygen. So that's what silica looks like if you look at it. So each silicon is going to form a tetrahedron like this. It's connected to 4 oxygen. So based on the formula that we saw last time, we can, based on that, find the coordination number of the oxygen. There's a relationship between the coordination number of the cation and the coordination number of the oxygen. The relationship is that the number of cation, which is M, times the coordination number of the cation is equal to the number of oxygen times the coordination number of the oxygen. So this is based on the fact that those 2 expressions gives you the number of bonds within the glass. So there's 2 ways to express the number of bonds. It's the number of cations times the coordination number of the cations, or the number of oxygens times the coordination number of the oxygen. So based on this, you have this relationship here between the coordination number of the cation and the coordination number of the oxygen. So in that case, if we apply this relationship to the case of silica, M is equal to 1. So let's replace m by 1. The coordination number of silicon, it's 4. Then you have the number of oxygen, which is 2, and the coordination number of the oxygen, that's what we want to find. So in this case tells you that the coordination number of the oxygen in silica is going to be 4 divided by 2, that is to say it's 2. So it means that in silica, each oxygen is connected to 2 silicon atoms. So in that case, those are what we call a bridging oxygen. It's an oxygen that is connected to 2 silicon atoms exactly. So that's the first thing. So now based on this, we can check the first 2 Zachariasen rules, because now we know the coordination number of the cation and the coordination number of the oxygen. So the first Zachariasen rules tells you that the coordination number of the oxygen needs to be 1 or 2. So here we find that indeed the first rule of Zachariasen is satisfied. We find that the coordination number of the oxygen is 2. Now we can check also the second rule. The second rule tells you that the coordination number of the cation has to be 3 or 4. And in that case, we find that it's 4. So it means that the second rule of Zachariasen is also satisfied. So now, if we want to check the third and the fourth rule, so now we need to see how many of the corners of the polyhedra are shared with other polyhedra, and how polyhedra, do they share corners, faces, or edges? So let's start with the fourth rule, because that's the easiest one to check. And here the fourth rule tells you that at least 3 corners needs to be shared. So it means that if you look at the silicon polyhedra here, so it's in this case it's tetrahedra, how many of those corners are shared? And here we found that all the oxygen have a coordination number of 2. So it means that all the oxygen will be connected to another silicon. So in this case, it means that in this case, you have 4 corners of each polyhedra, of each silicon polyhedra that are shared. And since you have these 4 corners, it means that the fourth rule of Zachariasen is satisfied. You have indeed at least 3 corners, in this case 4, that are shared with other polyhedra. Then the last rule of the Zachariasen rule to check is, are the cations sharing corners, edges, or faces? And here, if you want to check this rule, the question should not be, is it possible that 2 silicon atoms could share some edges or faces? The question here is, can you draw an atomic structure where you can avoid the formation of edges and faces? So of course, if you wanted to, you can always have 2 silicon that are connected to each other and share 2 or 3 oxygen. Like, there is nothing that prevents you from doing that. But the question here is, if the structure wants to avoid the formation of edge sharing or face sharing unit, can it avoid the formation of such units? And so what we will see is that in certain cases, when you draw the structure of glasses, you cannot avoid forming some edge sharing and face sharing units. And in that case, that's where the third rule would not be satisfied. So if you can draw the structure of a glass without having any edge sharing or face sharing units, if you can just draw it by using only some corner sharing connection between the polyhedra, then the third rule would be satisfied. So in this case, indeed, if you look at the structure of silica, you can indeed draw this structure in such a way that you never form any edge sharing or corner sharing units. You can always draw this structure in a way that each silicon will share at most 1 oxygen in common, but will never share more than 1 oxygen. You will never have to draw the structure in a way that it's going to share 2 oxygen or 3 oxygen. So in that case, it means that you can draw a structure that comprises only corner sharing units. And since this is true, then it means that the third rule, the third Zachariasen rule, is satisfied. So in that case, we find that all the 4 Zachariasen rules are satisfied, it means that silica, as expected, is a good glass former. It has a good glass forming ability since it satisfied all those 4 rules of Zachariasen. Second example is boron oxide, B2O3, where now the cation is boron with symbol B, and for each pair of boron, every time you have 2 boron, you have 3 oxygen atoms. So same thing, let's start with the coordination number of boron. So in this case, boron has a trigonal structure, so the coordination number of boron is 3. So in this case, the coordination number of boron is 3. This satisfied the second rules of Zachariasen that tells you that the coordination number of the cation needs to be 3 and 4. In this case, it's 3, so it means that the second rules of Zachariasen is satisfied. Same thing, we can now check what is the coordination number of the oxygen. So the coordination number of the oxygen, we can use the same formula as we saw for the case of silica. The coordination number of the oxygen is going to be equal to the number of the cation, which is 2, divided by the number of the oxygen, which is 3, times the coordination number of boron, which is 3. So in this case, we find that the coordination number of the oxygen is 2. Just like in the case of silica, each oxygen is going to be a bridging oxygen. It's going to be connected to 2 boron. So each oxygen has a coordination number of 2. That satisfies the first rule of Zachariasen, that the coordination number of the oxygen needs to be 1 or 2. In this case, it's 2. So now let's check the fourth rule. Let's check how many corners are shared. So here, if we look at this, so we find that the boron has a coordination number of 3. It is forming a trigonal structure like this. So this is the trigonal structure that is formed by the boron. And since all the oxygen have a coordination number of 2, it means that all of those oxygen are going to be connected to another boron. So they are going to be connected to another triangular structure like this. So in this case, it means that for each boron trigonal structure, it is connected to 3 other trigonal structure. It means that 3 of the corners are shared. So it means that this satisfies the fourth rules of Zachariasen. You have 3 corners that are shared. So this is enough. It satisfied the 4 Zachariasen rules that tells you that at least 3 corners needs to be shared. In this case, it's exactly 3 corners that are shared. And now let's look at the fourth rule, the final rule. And again, here the question is, can you draw a structure where you draw the structure in such a way that those polyhedra only share edges and never share, so they only share corners, never share edges or never share faces. And in that case, indeed, you can draw the structure by only having some corner sharing units. In this case, you can draw the structure in such a way that, for example, you have 1 boron here connected to 3 oxygen, and then this oxygen is going to be connected to 2 boron. So you can have something like this, for example, where the oxygen is connected to 2 boron like this, and then each of those borons are going to be connected themselves to 3 oxygen. So here you can have this, for example, this types of structure here that is called a boroxyl ring, where you can draw this structure like this, where each of the polyhedra, each of the triangular structure formed by the boron atom is forming this triforce structure here, where those polyhedra only share only 1 corner at a time. So each pair of polyhedra that is connected to each other is only connected, they only share 1 oxygen in common. They never share an edge, they never share a face. So in that case, it means that indeed we can have only corner sharing structure, and in that case it means that the third Zachariasen rule is going to be satisfied. So again, you have a case here where the four Zachariasen rules are simultaneously satisfied, and in that case it means that again B2O3 is going to have a good glass forming ability. B2O3 is a good glass former. It's very easy to form a B2O3 glass. So next example, sodium oxide. So in this case, sodium oxide is not known to form a glass. So we expect that this compound might not follow the Zachariasen rules. So let's check that. So in this case, let's assume that the coordination number of the sodium is going to be 4. So that would satisfy the second rule of Zachariasen. The coordination number of the cation needs to be 3 or 4. In that case, this condition is satisfied. So based on that, we can compute now the coordination number of the oxygen. Coordination number of the oxygen is equal to the number of cation that you have divided by the number of oxygen, which is 1, times the coordination number of the sodium. So here you would find that for this structure to work, if the coordination number of the sodium is 4, then that would give you a coordination number for the oxygen of 4 times 2, which would be 8. So in that case, it means that the first rule, the first Zachariasen rules, would not be satisfied. So in this case, this is a case where the connectivity of the glass, the coordination number of the oxygen would be too high, so that this structure would not pass the first rule of Zachariasen. So in this case, that's an example where we can find that this compound would not form a glass because at least one rule, there is only, even if even one of those rules is not satisfied, then this would not satisfy the Zachariasen rule. So in this case, we find that since the coordination number of the oxygen would be too high, there is no way that this structure could possibly form a glass. So now let's consider the example of calcium oxide or lime, CaO, where the cation is calcium, and you have, for each calcium, you have 1 oxygen. So in that case, let's take a look at the coordination number first. So the coordination number of calcium would typically be 6. So this alone, in that case, would not satisfy the Zachariasen rules, right? Because the coordination number here is larger than 4. The Zachariasen rules tells you that the coordination number can only have a coordination number of either 3 or 4 for the cation. So this means that rule number 2 would not be satisfied in this case. Just for the sake of it, let's look at what would be the coordination number of the oxygen in this case. The coordination number of the oxygen would be the number of cation, which is 1, divided by the number of oxygen, which is also 1, times the coordination number of the cation, which is 6. So in that case, the coordination number of the oxygen would also be 6, which means that, again, this would not satisfy the first rule of Zachariasen because the coordination number of the oxygen is too high. It needs to be only 1 or 2, but here it's 6, so it's far too high. This structure would be too connected. Just for the sake of the example, let's look at the other Zachariasen rules. So here, if we try to draw this structure, it would look like this. So you would have a calcium. Each calcium has a tetrahedral, an octahedral structure. It's surrounded by 6 oxygen like this. And now each oxygen itself has a tetrahedral structure. So it's surrounded by it's surrounded by 6 calcium. In the same way that each calcium is surrounded by 6 oxygen, each oxygen is surrounded by 6 calcium. So here, if you draw this structure here, you form this kind of structure like this. And so if you look at this, what about the fourth rule of Zachariasen? So here you would find that each of the 6 oxygen corners would be shared. Like each of those 6 oxygen is going to have a coordination number of 6, so it's going to be connected to at least 2 calcium. It's going to be connected to 6 calcium. So it means that in that case, the third rule, the fourth rule of Zachariasen, that at least 3 corners needs to be shared, this would be satisfied. In that case, you have a 6 shared corner. So that satisfied the 4 Zachariasen rule. So in this case, the 4 Zachariasen rule would be shared. What about the third rule? The third rule tells you that when you draw the structure, you need to be able to draw a structure where the polyhedra only shared corners, not edges, not faces. So here, if we look at this, is it possible to draw a structure where the 2 octahedra only share edges? Here, if you look at this, so here you have one octahedra here. So this is the octahedra around this this calcium, and so now you have this oxygen here that is going to be shared with another polyhedra. So this calcium here. So this calcium is going to form its own polyhedra. So with one oxygen here, there is one oxygen at the top, one oxygen at the bottom, and then you have one oxygen on the right, one oxygen on the left. So this thing is going to form its own polyhedra around it. So it's going to form its own tetrahedron structure. And if you look at this tetrahedron structure here, now they are forming necessarily they have to form an edge sharing unit. Here, those 2 polyhedra, they share necessarily 2 oxygen in common here. There is no way you can draw this structure without having polyhedra sharing 2 oxygen in common, sharing some edge connection. So here, that would be an example where you cannot avoid the formation of edge sharing units. And those edge sharing units, they are forbidden by the Zachariasen rule. It's forbidden. It doesn't satisfy the third Zachariasen rule. So in this case, since you cannot draw the structure without having some edge sharing unit, then it means that the third Zachariasen rule would not be satisfied. So in this case, calcium oxide would only satisfy the fourth rule, but it would not satisfy the first, the second, or the third rule. So this is an example of an oxide that would not form a glass because it doesn't satisfy all the Zachariasen rules. So we could see some other examples, but we will stop here. So here you have some example of substance that can form Zachariasen rule because they can form glasses because they satisfy each of the 4 Zachariasen rules. And on the other hand, if at least one rule is not satisfied, then the oxide would not be able to form a glass, or it would be very difficult to form a glass. So by simply checking those 4 rules, you can check if the connectivity is high enough but not too high. If you can have this sweet spot of connectivity where the glass is rigid enough to form a 3D network, but also flexible enough to form a disordered structure, this is what is checked by those 4 Zachariasen rules. And if a substance, an oxide substance, can satisfy simultaneously those 4 Zachariasen rules, then you know that the connectivity is high enough, but not too high. And in that case, it means that there is a good chance that this oxide will indeed be able to form a glass. If you melt a liquid and then quench it, it's going to be more likely to vitrify into a glass rather than crystallizing into a periodic crystalline structure.